about the kind of cosmology that you can do with Euclid. And basically, I will try to take you in a trip from the promise of this science, basically from the dreams of a bunch of people more than 15 years ago to the present, where this has become a reality. Now we have a beautiful satellite that is launched into space and is taking very nice pictures of the universe, as I will show later on. So let's get started with the trip. But before that, I would like to show this slide that you have seen probably 1,000 times, many of you, but just to set the scene. So basically, we know that we have a cosmological model based on general relativity. This is called the lambda cold dark matter model, that we believe that explains successfully a wide range of observational data from the deep universe and from the primordial universe in particular, but we still have a few open questions in this model. In particular, the main constituents of the model, of the lambda cold dark matter model, are not very well known. We don't know what they are. So we know that there is something we call dark matter. We believe it's a particle we have not detected yet that is responsible for the clustering of and the growth of structure in the universe. We have another component that we call dark energy that is believed to be responsible for the accelerated expansion of the universe, but we haven't detected this dark energy directly. There is no physical evidence for that. So there is I would say, the possible alternative to this model, which is that general relativity is breaking down on the largest cosmological scales, and we have to decide whether this is true or not by exploring further in the universe. There is also the well-known tensions in the measurement of cosmological parameters, in particular the expansion rate of the universe and the parameter that measures the amplitude of fluctuations that we call S8, depending on whether you use cosmic microwave background data or galaxy surveys, okay? This is a significant tension, but you have to think that these two observables, the early universe and the late-time universe, basically they use the same model, which is extrapolated by a factor of 1,000 in scale factor, okay? So it's not completely surprising that the model may fail, okay? So we want to investigate and basically settle down these questions for good by exploring a larger volume of the universe with very high quality data. And this is precisely the motivation for Euclid. It's a mission, a cosmology mission, to study the universe, in particular the gravity and the nature of dark matter and dark energy. Okay? So this was a mission that was happily selected by ESA about 12 years ago, and it's a medium-class mission. So at the time, basically when the mission was proposed, there were a number of goals which has evolved in time, but basically the main science goals are these ones. So we want to understand what is dark energy, whether it's constant in time or whether it evolves in time, okay? So this we don't know yet. And that's why Euclid is going to explore the high redshift universe to see if there is a possible evolution of this so-called dark energy equation of a state, okay? We also want to test gravity. As I said, we want to measure tiny deviations from the predictions of general relativity. And at the same time, we want to test this cold dark matter paradigm that we believe is explaining all the range of observations, as I was saying, and also to constrain the total mass of the neutrinos that we believe now are part of the standard model of cosmology, okay? Especially when we combine it with Planck. And last but not least, we want to improve by at least an order of magnitude the initial conditions, the measurement of the initial conditions of a structure formation in the universe, and in particular, basically constrain the inflationary models that we believe seeded the structure formation in the universe. Okay, so this is the Euclid mission in a nutshell, let's say, in numbers. So the Euclid consortium has grown exponentially since it was adopted. So at the time, there were just a bunch of people, about maybe less than 100 people in the community. And then with time, this has surpassed the 2,000 members. And this is the size of today's galaxy survey collaborations. There are more than 300 institutes involved. It's 13 European countries, so that's basically the bulk of the Euclid consortium. But there is also a component from the USA, Canada, and Japan, which is also contributing to the project. And the main objective of this consortium is to lead the two instruments, the visible imager and the near-infrared spectrophotometer, along with a pipeline, the scientific pipeline that is going to reduce and distribute the science data ready products of the mission, okay? There is also a very important component from industry. Obviously, without industry, we cannot build any instrument. So there are about 80 European companies participating. So there's a clear impact on the economy, on science, I would say, in this aspect. And then in terms of the survey, Euclid will map basically 1/3 of the sky. So basically the cleanest regions of the extragalactic sky with a resolution, a spatial resolution, which is comparable to that obtained by the Hubble Space Telescope. So this is 4 times sharper than any ground survey. The end product of the mission comes basically in 2 flavors. There will be a photometric sample containing more than 2 billion galaxies, basically up to redshift 2.5. And then the spectroscopic sample, which contains about 30 million galaxies. These are emission line galaxies in the range between 1 and 2, as I will show later. Okay. So now, let me just emphasize the fact that the Spanish contribution is very significant and has been prominent since the start. So I would like to mention 2 people that were key in order for Spain to get into the mission. And these are Francisco Castander and Rafa Rebolo. So the 2 Spanish representatives, they were there from the start. They were pushing really hard for this to happen. And today, we are basically have commitments to actually deliver something for the project, also thanks to them. So there is a multilateral agreement between ESA and the Ministry of Science to contribute both on the instrument and on the ground segment simulations, okay, the image simulations. So we have responsibilities there. In particular, IEEC, and IEEC in Barcelona are contributing to the design, construction, testing, and validation of the filter wheel assembly of the near-infrared spectrophotometer, and then the Universidad Politécnica de Cartagena, along with the Instituto de Astrofísica de Canarias, are also contributing to the design, construction, and validation of the electronics of this instrument. Okay, so this is a very important contribution from the Spanish community. There are about 170 researchers, counting everyone in terms of engineers, scientists, across 22 institutions. So this is about, or close to, 10% of the overall consortium. So this is a very significant portion of the Euclid consortium as a whole. And we have a leading role in coordinating both science working groups, like the cosmological simulations in which I'm involved, IST nonlinear, which provides a model, nonlinear model, theory model for the observables, and leading roles in the science ground segment, image simulations, the science data center, one of the 9 science data centers of Euclid at PIC in Barcelona, and then management roles in all the bodies, basically, from science team, Euclid board, editorial board, and speakers bureau. Okay, so it's a very prominent role. Now let me go back to the instrument. So Euclid is optimized for wide field imaging and spectroscopy. It's quite unique in terms of wide field of view with very nice spatial resolution. This is unique. This is showing basically the projection of the visible imager on the sky, so it's wider than the moon, so that you have an idea. So the field of view is 0.7 by 0.7 square degrees. As I said, the visible imager contains 36 CCDs. The resolution is 0.1 arcseconds per pixel. This is very fine resolution, enough to measure the shapes of very distant galaxies at very high redshift. This is an exquisite, I would say, spatial resolution. It uses just a broad band in the visible from 500 to 900 nanometers, whereas the NISP, the near-infrared spectrophotometer, has a lower number of CCDs with lower resolution. Basically, overall, it's a factor of 3 lower resolution, still quite good resolution, and basically has 3 bands covering from 900 to 2,000 nanometers. Okay? On top of that, we have the slitless spectroscopy capability with very nice resolution. So basically, we can combine from this instrument both infrared photometry and spectroscopy. Okay, this is just a quick comparison of how Euclid field of view compares to other surveys. So you see on the right JWST and HST, which are less than 1% of the field of view of Euclid. And then you see that the only survey that actually compares in terms of wide field of view is the Roman satellite that will be launched in a few years, but basically will be complementary to Euclid. It will go to the far infrared. Okay, so nothing really compares at the moment to Euclid in this combination of wide field of view and spatial resolution. So these are the bands I basically commented, so you can see the distribution, the visible from 500 to 900, the two photometric bands of the NISP in the different colors on the right, from 0.9 to 2 microns, and then the blue and red grisms of the spectroscopic part of the instrument that cover pretty much the same wavelengths. Below you see, you see basically the limiting magnitudes for the wide field is 24.5 in the visible, 24th in the near infrared, and the deep field goes 2 magnitudes deeper, okay? And also it goes deeper in terms of spectroscopy. Okay, so just a couple of words on the instruments. I don't have much time, just for you to keep in mind that the visible imager is devoted to getting very accurate images of galaxies and their shapes. So this means that the instrument has to be very stable and very simple, okay? So that there are no moving parts, and that's the bottom line. This is a very simple instrument, okay? On the other hand, the NISP is much more complex because it has to basically conjugate the two kinds of observations, the photometric part and the spectroscopic part. So basically, this has moving parts, let's say, and it has two wheels, one for the filters and the photometry and the grisms. So this is much more sophisticated, and this is the main instrument, again, for galaxy clustering, okay? So 2 instruments for 2 different kinds of science. This is the optical layout, how the beam crosses the baffle on the top left, through the mirror, bounces in several folding mirrors. The basic thing is that it goes to a dichroic that splits the beam. One part goes to the NISP, and then the other part goes to the VIS. But basically, the idea is that both instruments observe the same region of the sky simultaneously, okay? You see on the right how the light path looks on a real picture, let's say on a picture of the real satellite, upside down, but it's a bit more complicated. This is how the satellite looks when it was integrated by Airbus about 2 years ago. You see the baffling system in white, the instruments at the bottom on the left. Then you see the solar panels, basically. You can imagine the satellite revolving in this way as it basically circulates or orbits around the sun solidary to the Earth, and the light from the sun will basically impact the solar panels that you see in black here at 90 degrees, okay? That's how it operates. Okay, let's go for the promise. So this is what Euclid promises to deliver, okay? 2 different surveys. A wide survey covering about 14,000 square degrees in the sky. It's going to avoid basically the Milky Way plane that you see in this Z shape in this projection, and also the ecliptic plane to avoid the zodiacal light, okay? The rest of the sky is the region that Euclid wants to observe for the wide footprint. Okay, and it's going to proceed from the ecliptic poles and advancing down to the ecliptic plane. So in different colors, you see the areas that are going to be covered in the different years of the nominal lifetime of the mission, starting basically from the green around the ecliptic poles and ending in yellow in the 6th year of the mission. So overall, it's 6 years in the nominal mission. I just wanted to mention the fact that there will be also deep fields. They will cover small regions close to the ecliptic poles, around 50 square degrees in total, and this will be used more for legacy science and for calibration. And there will also be photometric information that cannot be obtained from space with Euclid, will be supplemented from the ground, okay? This is very important in order to achieve the science. So we already have covered all the information in the visible and in near infrared from DES, unions, and LSST. So LSST basically covers the south and slight part of the north, and then unions basically on the north, DES also on the south. So we have all this in place, and we are ready basically to combine it with the data from the satellite. This is a summary. I'm not going to go through this, of the Euclid wide and deep surveys in terms of how many galaxies you will get, about 1.5 billion galaxies for the photometric sample, 35 million spectra for the wide survey as well, and for the deep, the numbers go down dramatically, obviously because these are small areas, but still 1.5 million galaxies in photometry, 150,000 spectra in, well, from the NISP. Okay. So let's go to the cosmology and the science itself. So cosmology, as you know, is mainly probed by measuring the expansion rate of the universe and the growth of structure, Okay, these are the two main things you want to measure. And with Euclid, we can pin them down with two different observables. So the gravitational lensing, weak gravitational lensing, that basically measures the distortions of light rays from distant galaxies as they traverse the intervening dark matter. Okay? So that distorts the shapes of those galaxies, and with that we can recover the dark matter intervening between those sources and the observer and the growth of a structure. From galaxy clustering, basically we assume that light traces mass. So basically by measuring very accurately the positions of galaxies, we can actually reconstruct the underlying dark matter in 3D, ideally with a spectroscopy, and therefore to be able to constrain the expansion rate of the universe, in particular with the baryon acoustic oscillations in the galaxy power spectrum, and the growth of a structure through the redshift space distortions, so through the velocities of those galaxies. Okay, so let's move to Euclid weak lensing very quickly, just to compare the performance of Euclid with current surveys. So this plot basically summarizes what is the situation. So in the x-axis, you see the redshift depth of all these surveys today, KITS, DES, and HSC, the best surveys for weak lensing from the ground. And you see that Euclid is going to basically outperform all of them significantly, both in the number density, which you see in the y-axis, at low redshifts, but also extending the redshift depth by almost a factor of 2, okay? So this is a significant step forward. I'm not going to talk about all the work that the science ground segment is doing so that you can actually get these clean shapes of the photometric sample of galaxies, but there is a lot of processing involved in order to clean all the astrophysical and instrumental systematic effects before you can actually do cosmology, okay? So I will save you that. At the end of the day, this is the forecast, the projection of how the statistical error bars will look like for Euclid, that you see here in black, in comparison to the current surveys, okay, in color symbols. So the bottom line is that for the overlapping redshifts, basically redshifts below unity, we are basically getting error bars which are an order of magnitude smaller than current surveys, but we are also extending the redshift range, as I said. Okay. How am I doing? Anyway, okay, so I should speed up. So galaxy clustering. So we are going to use this slitless spectroscopy. Basically, this means, in simple words, that we are not going to use predetermined targets in which we put fibers, as it happens, for instance, with DESI, but we are going to observe all galaxies. We are going to get all spectra for all galaxies in the field of view. And this obviously is a new technique that is very noisy in a way. So basically you get these very messy images that you see on the top. Here basically you see, oh, sorry. So we should do like this. So basically you see these very bright features in columns of the CCDs. These are light dispersed from many galaxies at the same time, okay? So we need algorithms that are able to, from these images, to recover the spectra at every pixel from many different galaxies, okay? And this is achieved because we have the flexibility in the Grism orientations to do this sort of inversion problem. Anyway, I won't go into that. The bottom line is that we can actually use these images to end up with 3D positions of the galaxies, very accurate ones, okay? This is hard, but it's doable. So if we do that, basically we can end up with this measurement of the power spectrum in redshift space, for which we can measure the baryon acoustic oscillations and analyze the full shape that is called of these two-point statistics to constrain the expansion rate and the growth of a structure. I forgot to say that this is on the left how Euclid compares in terms of volume and number of redshifts with all other current or existing surveys. As you can see, only DESI really compares to Euclid in this sense, but actually Euclid is a bit denser over the volume that it occupies. So it's basically the best survey for this, along with DESI, I would say. So this is the $1 million plot in terms of forecasting. It's not yet the data. We hope we get there very soon. So the basic idea is that we are going to combine, as I said, these two main cosmological probes, weak lensing and galaxy clustering. And when you do that, that's the power of Euclid, is the fact that you are going to use probes which are, very small statistical error bars associated to them, but especially when you combine them, you are going to break the degeneracies that affect those probes separately, okay? So basically, you are going to constrain cosmology way farther than with these probes separately. also because when you combine, you are less sensitive to the systematic effects that affect those probes individually, okay? So it's both statistically and in terms of systematics that this probe combination is key, okay? So at the end of the day, we're going to get 1% error bars on the basic lambda CDM parameters. This is comparable to the precision of Planck itself. So it's the first time that the galaxy survey is actually comparable in constraining power to a CMB experiment like Planck, okay? And we are going to do better in terms of dark energy constraints than any other previous experiments combined, okay? In particular, for the time evolution of dark energy, this is the first time that we'll be able to constrain it with 10% accuracy. So something that is really precision cosmology, we can say. And obviously, if the lambda CDM model is wrong, we will also be able to see it clearly. And we can pin it down with a few percent accuracy. I'm not showing this here, but this is going to happen as well as part of the analysis of Euclid. Okay, there's much more. I don't have time to go through this. So, but there is cluster cosmology, it's not the main probes, but there will be about a million clusters, massive clusters to be observed up to redshift 2. This will allow to constrain dark energy by a factor of 2 better than any other cluster survey so far. There is also strong lensing. So we will see galaxy-scale lensing systems of the order of 100,000 at intermediate and high redshifts that cannot be detected from the ground. This is very important. And if we combine it with weak lensing, we'll be able to reconstruct the cluster profiles, okay, from kiloparsec to megaparsec scale, so 3 orders of magnitude in scale. Many other things, AGNs, quasars, massive galaxies at high redshift, all these will be completely, basically, outperform any previous surveys. And of course, just to mention that the legacy value of the mission for astrophysics is huge. Basically, just from serendipitous observations, you will be able to get 100,000 solar system objects, but also you can study local universe, transients, and so forth. There is a lot. I'm not working on that, but this doesn't mean that it's not interesting. There is a lot of legacy value that people will get from this data set. And there are many people, in Euclid interested in this kind of science, and I think it's a very valuable part of the mission. I don't know how much time do I have? 3 minutes, excellent. So just to say a few words about the simulations. I will not talk about this. If there are questions, I will mention later. But this is a very important part of the scientific preparation and exploitation. So we start from state-of-the-art simulations, dark matter simulations. We identify dark matter halos. We populate them with galaxies, with observational recipes. And then we fold in the survey footprint, instrument-specific noise and characteristics, and then with that high-fidelity galaxy mock, we can actually develop the scientific pipelines that later on we will use to analyze the data, okay? So thanks to these mocks and thanks to the degree of realism of these simulations, we are ready to actually analyze the data in the correct way, okay? So this is just giving a few of the specs of the simulations we're using, involving trillions of particles over large cosmological volumes, going to high redshift. I don't have time to go through this. This is the pipeline that is running at the Spanish data center. This is a beautiful, massively parallel platform with which, when we apply this galaxy assignment step to the dark matter simulations, we can generate billions of galaxies in just a few hours, okay? When the mock is calibrated, so the free parameters of the mock are calibrated. But this is huge. I mean, there is nothing like this, to my knowledge, in any other collaboration. Okay, so this is the end product. This is just 1 octant of the sky, 5,000 square degrees, more than 3 billion galaxies up to redshift 3. Hundreds of galaxy properties per galaxy. make the numbers. And this is just, all galaxies in a stripe through the light cone, the visible and the NISP. I think the quality of the image is not very good. Sorry about that. Weak lensing, measurements in the simulations, comparison with theory. Again, I don't have time to go through this, but we have done the full exercise of determining the power spectra or the 2-point correlation functions from the galaxy clustering and weak lensing. And we have shown that with the models, with the theory models that we have developed, we can actually recover from the simulated data the input cosmology, okay, with high precision. And this is very important because, as I said, this will be used with the real data in the same way. So the fact that we have the theory model, the fact that we have the right simulations, this makes us feel confident that we can now actually analyze the data correctly. So these are all the properties that we have for the simulations per galaxy. You can find this mock at Cosmo Hub, and this is the paper describing the simulations, if you are interested. Okay, 2 minutes for the reality. Sorry about that. So basically, the satellite, as you know, was launched last year in July from Cape Canaveral. It was injected into the Lagrange 2-point orbit. It's 1.5 million kilometers from the Earth. So we completed the commissioning phase, the performance verification. The instruments are performing better than nominal in sensitivity, so people are really, really excited about this. There have been problems, obviously, with the straight light, with the magnificent solar activity that has been recently in terms of X-rays, which was really a pain in the neck for the science ground segment, icing in some of the mirrors. So this has been largely solved by software. So now everything is back to normal, working very nicely. We have 5 months of data already collected. We have pictures like this. So this is the Perseus cluster. This is an image that was released last November. It shows a cluster that is about 100 megaparsecs away with 1,000 galaxies as part of the cluster in the foreground, and about 100,000 galaxies. And for half of them, we can measure accurate shapes. Okay, 50,000 galaxies is just one field. And we are going to obtain about 40,000 of these pictures across the nominal survey. If you make the numbers, 50,000 by 40,000, that gives you, more or less, the 2 billion galaxies with accurate shapes, just with this simple exercise. It's a rule of thumb. So basically, the promise, I think, is becoming now a reality, right? There are other images like this spiral galaxy. This is in the plane of the Milky Way, and it's face on. But we can observe it because we have the infrared channel, right? So we can actually see through the dust, and we can get these very nice images. This is a composition between the visible and the near infrared, and you can do some galaxy evolution studies with it, okay? So I finished with the timeline for the survey. We have started already. The data release 1, including 1 year of data, will be delivered to the collaboration in June approximately next year, summer next year. 1 year later to the full community. Then there will be data release 2 years later in 2027. And then the final data release after collecting the 6 years of data in 2030, if I'm not mistaken. There are discussions whether the mission can be extended if there is fuel and there is money to maintain the mission. So basically, we can extend the nominal final area of the survey, which is about 13,000 square degrees, to complete these 14,000 square degrees that were promised. Again, we want to fulfill the promise. Okay. So I will stop here and will leave you with a few links if you want to get more information or follow the day-to-day activity of the project from the social media. If you're interested in the papers presenting the EROS, the early release observations that I showed, or the papers presenting the mission, they are on the archive. They were submitted last May. Okay, thank you.
So thank you very much, Pablo. It's time for questions. 1, 2 questions. I cannot see from here, so.
Any questions? Here, there's a question. Okay, the extension. Okay, so it's the plan. I mean, this is under discussion. So the idea is that, as I said, because there have been these problems with the straight light and so forth, and with the X-rays, so part of the visible CCDs have been slightly damaged. So this means that the effective area that we can cover in the 6 years doesn't reach the 14,000 square degrees. And therefore, we want to actually, in order to fulfill the figure of merit that I showed in that forecast for the combination of the main cosmological probes, we need ideally to extend beyond the 6 years. So, I mean, the possibility is that we can extend up to 2 years, maybe, and we can go beyond 14,000 square degrees. But this is under discussion of whether, I mean, we want to do that or we want to prioritize some other things, like the deep fields. I mean, there is a wide range of science that you can do beyond just extending the area, right? So there is a scientific discussion going on at the moment in the board, in the Euclid board, to decide what is going to happen with the science team, obviously. So this is not yet fixed, but there seems to be a plan for go beyond the 6 years of the nominal lifetime, yeah.
Thank you. One more question?
Yeah.
Sorry, a very fast one. Maybe I misread, but I thought that you said that the data release for the Q1 was November 2024?
Sorry? The release.
The
release.
release.
The release
the
one.
Q1.
So there will be, well, first of all, there will be the Q1, it's called. This is just a small patch of the data that will be released in fall this year. But this is just for like legacy array science, let's say. Astrophysics, not cosmology. So the cosmology release is data release 1, which is going to be summer of 2025. This is for the Euclid consortium. Internal release, there will be 1 year for the community within Euclid to analyze the data, produce the papers, just 1 year. And then in the summer of 2026, the papers along with the data will be published, okay? So this is very stressful for the Euclid community, but this is the schedule that we promised. Yeah.
Okay, thank you.
So thank you very much, Pablo.
Okay.
We can...